A little bit about me and why I'm here. So I'm a longtime schemer. When I was deciding where to go to grad school, I looked at my bookshelf and I saw that almost all my computer science books had authors from one university. So I decided I need to move to Indiana to go work with Dan Friedman and those people. Though these days I primarily work with types and Haskell, but still a schemer and a Lisper at heart. So what I do in research primarily is I apply functional programming to like low-level problems. So things that you would ordinarily need a language like C or C++ for, right? And I know this might be a little bit offensive to this crowd, but I also believe in using types to make programs faster, right? And of course, by the end of this talk, everyone here is going to agree with me that types are great. I'm sure that's going to happen. Okay, so the work I'm going to talk about here is not just me. It's a bunch of other people across several universities, Indiana, Purdue, Carnegie Mellon, and also Facebook. I guess it's Meta now. Right? Okay, so what do I mean by programming with serialized data? Right. Here, I have an example here. There's a picture of a binary tree on the left. I guess I have to avoid the impulse to go to the screen because that doesn't work for the streaming. So on the left, there's a binary tree, right? And on the right, I have some pseudo C code for like defining how you might define this as a struct, right? So the big idea here is we have individual heap objects for the nodes and the leaves, right? And they're connected by pointers, right? So the node here, that's the root. The left child is a pointer to this leaf, and the right field here is a pointer to this subtree, right? So in languages like Java or whatever, you have something similar with additional, header information for garbage collection, whatever, right? Most programming languages, this is how you'd represent something like a tree, right? And in fact, in a nice programming language like Racket, we could write it like this, right? And say, well, a struct leaf contains an element, a struct node contains left and right, and we can build this tree using this as expression, right? This is very nice and convenient, right? So thinking about this, in my research group when I was a PhD student, my supervisor came in and said, okay, today we're going to talk about how we can traverse a binary tree the fastest possible way, right? So given that sort of data structure, what I want to do is I want to walk through the entire binary tree, iterate through every leaf, and increment the number in the leaf by 1. What is the fastest possible way I can do this, right? So starting with very high-level languages and getting more and more optimized. So for a while, this was the reigning king. This is implemented in Shave Scheme, right? If you are a Shave Scheme wizard, you might recognize this funky-looking symbol here. This is optimized 3 fixed num addition. Also, the optimization of using pairs to represent these nodes because the compiler is very good at handling cons, right? So this was significantly faster than anything in Java. It was faster than implementing this ordinarily in C++, right? We didn't test SVCL. I'm sure it was comparable performance to this. But we wanted to get even faster. So the key to getting faster was to change the memory representation, right? So what if instead of this structure on the left with all the pointers, we represent the tree as this serialized binary tree on the right? It contains the same information, right? This is a pre-order serialization of that binary tree. So how does this work, right? Well, the tags, right, the N and the L tags, they're in line in the data, right? And in fact, the entire subtrees are in line, right? So this subtree here that contains the leaf with 1, this follows immediately after the node tag, in line in the data, right? Right? But did we lose the structure, right? Now we just have a bunch of bytes. So there is still structure here, like we as humans can see and look at it, right? But the computer doesn't necessarily know, right? And maybe more importantly, the compiler doesn't know. It can't help us anymore because we've lied to it and said this is just char star. Right? So we want to implement add 1 on our binary tree. Ideally, what we want to do is walk through element by element without having to allocate any nodes or leaves in the heap, right? So we don't want to parse it first, and then we don't want to reserialize it afterwards. Okay, So why would I want to do this, right? Well, it's not just because I care a lot about incrementing leaves and binary trees, right? So one of the main motivations here is for an application that deals with data that was, for example, written to disk or sent over the network. Ordinarily, you have to deserialize it to put it into whatever format is convenient to use in your high-level programming language. Then you would apply your function to it, and then you'd have to reserialize it to send it back wherever it came from. Right? So it would be nice if we could save a little bit of time and just apply the function directly to the data as it exists without having to marshal it first. So another reason, and in fact this was the original motivation, was we could just get really fast traversals. Right? If we serialize the data in the order that we intend to traverse it, then we don't have to follow all these pointers around. We're basically going through the data in the order that it exists in memory. So we get better locality. We don't have to spend extra time chasing down indirection. Okay, so seems great. I hope I've convinced you this seems great for at least this narrow use case. So what is the catch? Well, the catch is this. Okay. So I'll give you a little bit of time to absorb this. I will be quizzing you on this C++ code. So make sure you understand it. Right? We good? Everyone's good? Okay. So basically here we're implementing add one. Like I said, it has to take in pointers to in and out. And oh, wait. Did anyone remember what was on that line? So what does this function do now? This is it's valid C++, it'll compile. So the line that I killed here was incrementing these pointers. So you will just end up with corrupted memory if you leave that out. So this is an incredibly simple program, basically, but it still has very subtle possibility for error, right? So what we want is something that doesn't have this downside, like functional programming, where we just write out exactly what we want the function to do, and then we let the compiler worry about this. Right? So this leads me into Gibbon and the location calculus. Right? So Gibbon is a programming language that I designed. It's a high-level programming language for programming with serialized data. Right? So it is statically typed. Again, I'm sorry. Right? It's a functional programming language with algebraic data types and pattern matching. Right? So you describe an algebraic data type, right? And then you use match statements basically to recursively break down and process the data. It has two front ends, one in typed racket, which I misspelled here, and one in Haskell. And for this talk, I thought I would try to be the pander to the audience a little bit and focus on the typed racket front end, so you don't have to read Haskell. Right? And I'm going to spend a lot of time talking about actually the intermediate language in the compiler. So local, or the location calculus, is a typed intermediate language that is used inside the compiler, right? And it actually has a fairly sophisticated type system, which is used to verify some of the invariants that we need to keep track of to make sure that we generate valid code. Right? Okay, so this is add one tree implemented in Gibbon. Right? If you've seen typed racket, this might look a little bit familiar. We have a couple of additions here. We have this data form at the top, which is like data declarations in Haskell or ML. Right? This says basically a tree is either a leaf with an int or it's a node with two trees. Right? And we have to annotate the parameter here of our function. Say the parameter to add one tree tr is of type tree. And the result, we return a tree. I just noticed the color is really off. Oh well, it's still readable. We use a case statement here to break down the tree. And it's either a leaf or a node. In the leaf case, we build a new leaf by incrementing the leaf by one. Otherwise, we recursively process x and y and build a new node. So this should seem more or less familiar, right? It's a room full of Lispers, right? So to get this out of the way, because I don't like spending a whole lot of time talking about evaluation, I put preview here, see the paper, see the full evaluation. I'm not going to go over all of our methodology for measuring things, but our performance is excellent. Right. So here, this is an aggregated tree traversal benchmark. A couple of different points of comparison up here. This written pointer, that's idiomatic C. Right. We also do Shea Scheme, Glasgow Haskell compiler, Java, Milton OCaml Racket, and this line down here at the bottom, this is Gibbon. Right. And if you notice the axis going up and down here, this is a log scale. So we're often 10x faster than some of these other languages. for this relatively narrow case of a recursive traversal of a tree where we fix the traversal order ahead of time.
What's on the x-axis? Is it tree depth?
Yeah. This is like size of the tree that we're making. Basically, it's not like literally size. You can see the paper, but there's a parameter that's like for generating a tree, basically, and it's measuring the size. So as we go from left to right, we're getting bigger.
The slowest implementation is what?
The one at the top, if I remember, is OCaml. Yeah. Yeah, and then Milton is the closest to what we're doing, which makes sense as it is also a whole program compiler like Gibbon. Okay, and then another point of comparison here briefly. This is on the other use case of, dealing with data without having to parse it. This is comparing against Cap and Proto and CNF, which are two different approaches for dealing with essentially data without having to read it in and marshal it first. I don't need to go into the details too much here, but this is like, it again shows that especially Gibbon compares very well to Cap and Proto and CNF, right? Okay, so getting into how this works, right? So the way that the location calculus works internally for the Gibbon compiler is it's based on what we call symbolic locations and regions. So regions are an old idea in programming language theory. They go back to like 94, Toft and Talpin. And locations are essentially symbolic indexing into these regions. Okay? So the reason we care about this is we need to translate our high-level function into low-level C, right? And so internally in the compiler, we have to keep track of pointers, right? But if we just change all of our function, objects, whatever, into pointers immediately, then we're not able to ensure that we're treating the pointers correctly, right? We might not be doing arithmetic on them correctly, right? So Gibbon uses these locations and regions to keep track of the serialized data in the heap, right? So symbolic locations point to positions inside regions, and regions contain serialized data, right? So these are our mathematical tools for reasoning about the state of memory, right? So the way that we handle symbolic locations and the types is every packed type is annotated with a symbolic location. So here, this list ls, this is at location loc, right? This is how it would be represented internally, right? And every application of a data constructor is annotated with the location it's going to be written to, right? So this cons call here, it takes in this special first parameter, which is where we intend to write that cons. Right? And locations are lexically scoped and are introduced with the special letloc form. It's similar to the let region form from region calculus. Right? And as a programmer, you don't have to write any of this. Right? So this is all inferred by the compiler. Right? So why are we doing all this? Well, locations are kind of like pointers, but there's a limited set of things that we're allowed to do with them. Okay? So a location can be, for example, at the start of a region, where we would declare it to be start R, right? So C equals start R, because it's the first thing in this serialized data structure, right? We can do arithmetic to them, as long as the compiler can prove that what's happening is safe, right? So this location A is C plus 1. If we tried to do C minus 1, that would be rejected. That would not be allowed. And then we can also get the location after some arbitrary other data structure. All right, so here, B is after A. You can say, well, why can't I just, add 2 to it, right? Well, we can use after to jump over things that were generated recursively, so we don't know statically how large they're going to be. Does that make sense? Okay, so go through a concrete example. And I think to make sense of this, I think it's easier to explain with an example of writing a serialized data structure rather than reading it. Right, so we can see how it's built sort of piece by piece, and that we maintain the sort of invariance of the heap as we build it. Okay? So to begin with, let's say we have some region R in scope, and we introduce this location C to be the beginning of this region. Okay? Right? We can leave a space for the node tag we're going to write, and introduce another location A afterwards. We can write a leaf to location A. And now in this picture here, you see if we look at location A right here, it does in fact contain a leaf with the number 1. All right? But we can use that after form from the previous slide to get the location after that leaf. Write a leaf containing the number 2. And then finally, we can construct the node. So, does anyone have any guess as to why we wrote the n last? Right? If it was just an array, you'd write the n first, right? But if you look at the program on the left, which does not have matching parentheses, I apologize. Look at the program on the left. Well, we couldn't write the node up here because we didn't have the x and the y. Right? So that's the functional programming intuition. The type intuition is if we had just the n by itself, that would not be a valid serialized data structure. So the heap would be in an invalid state. Right? Okay. So this beautiful piece of code is the locale representation of add one tree, which again, you don't have to write, but I'm making you read it anyway. So can you see that? Yeah, little boxes up there, right? This is not exactly how it would be written. I sort of sanitized this a little bit to make it fit on a slide. But there are a couple of introductions here. So at the top, we're binding these locations, LA and LB. These are arguments to the function. I thought about writing for all here, but I thought it would be intimidating, and then I just said it anyway, so I'm sorry. And then our parameter here, the tree, this is annotated to have the LA type, and the return tree has the LB type. And if you look at the tail positions of both of the cases, right? In the first case, we are in fact writing a leaf to LB. And in the node case, we are in fact writing a node to LB. So we've satisfied the return type. Now, what about this big mess in the middle? So if you look closely at it, this is basically the example I just had on the previous slide. But instead of writing a singleton list, we have a recursive call. Right? So we introduce this location LH, which is LB plus 1. We do a recursive invocation of add one tree that is going to write to LH. We introduce this LJ after LH. We do a recursive invocation of add one tree that's going to write to LJ. And then finally, we write the node. Does that make sense? How this is basically what we did before, but with recursion? Right? Yeah, and because these things are built recursively, there's no way to know ahead of time how big they're going to be. Right? So that means we need some way of keeping track of that in the language. And I'll get to that in a little bit. Right? So like I mentioned earlier, there are valid and invalid serializations, and we want to avoid the invalid ones. So the one at the top here, this is invalid. We never want our program to be in this state, where we claim we have a node that has arguments x and y, but then if you go look at memory, right, well, we've written the first one, but not the second. So we want that to prevent, we want to prevent that. So the value at C, if we say there's a node at C, it needs to be a valid serialization of whatever type it's supposed to be. All right? Okay, so that leads into, I'm going to talk a little bit about the theory. Right? So the invariant that I just mentioned here is that, so if we have some expression E, it has type tau at location loc, and that's in scope, then the location in memory represented by that symbolic location should have a valid serialization of a value of type tau. So that was a mouthful. Does that make sense? Right? Okay. And the way that we do this is we use types. Right? And types are not just, a restriction here to make things harder. Right? We actually produce these programs, these annotated locale programs, using type inference. Right? So this is an analysis the compiler is doing, which we've phrased as type inference, as a way of doing it automatically. Right? So we also ensure that locations are only written to once. So this is a functional programming language that gets turned into an imperative programming language. If you write to a location more than once, you're going to screw things up. Right? And we also constrain how locations are used in order to maintain this invariance. Right? So let's look at a few examples. Right? So this is from that slide earlier. We can check our invariant on each of these bound concrete values. Right? And in each case, we can look at, okay, so this is supposed to be at location A. We can look at where that is, and yeah, there's a valid tree there. Similarly here for B, and then for C. So we were always maintaining our invariant in each of these cases. Right? Okay. Now there's going to be a little bit of LaTeX. So I'm going to talk about the dynamic semantics. Right? So we use a small step operational semantics. It takes steps with the store, map, and expression. Right? So M, the map, this is a map from symbolic location to this region index pair, just like a pointer, basically. Right? It's like which region and then how far into it. Right? And then the store itself is basically the heap. This maps regions to chunks of memory, right, which are indexed by natural numbers. Right? So as an example here, let's say this is our heap. We have one region, and it contains a singleton leaf. Right? In fancy math mode, we'd write it like this. Right? S equals this region, which points to index 0 is L, and index 1 is 1. Right? And then our map says, well, location A maps to this point. Does this make sense? All right? Okay, and then everyone's favorite, typing. So this gigantic expression down here, this is our typing relation. We have all of these letters. I'll go through them briefly. Right, so gamma is the usual typing environment. Sigma is location type. So this maps symbolic locations to what type they're supposed to be. Right, then these other three letters, A, C, and N, so this is sort of where the magic happens. So we're keeping track essentially of the state of the heap in the type. Right? And A contains what is the sort of location at the end of a region. So we're always sort of writing on the end of it. So we have to keep track symbolically of what's on the edge of the region. C keeps track of symbolic constraints on locations, right? Like which locations after what other location, right? And then N is a set of unwritten locations, right? So we're only allowed to write to a location if it's unwritten, and we can check in the set to make sure, right? So as an example here on the right, we want to type this simple expression, which is just a variable reference. How do we know this variable reference is the type and location that it says it is? Right. Well, we would need to check gamma first to make sure that it is that type, and then we need to double check sigma to make sure the location agrees with it. Right. Okay. So now to go into a little bit more detail, I'm going to spend the rest of the talk going over this in excruciating detail. Right. So everyone needs to pay attention because I will be quizzing you on all of these typing rules. This is just the first half. Everyone's good? Right? Okay. No, I'm just kidding. I'm not going to make you do that. It was bad enough that I had to do it. Right? Okay. So instead, I'm going to go through an example. Right? This is the same example, but now instead of seeing a picture of the heap dynamically, we're seeing the type state and how it represents what is going to be in the heap, if that makes any sense. Right? So these types symbolically represent what's supposed to happen, and the contents of these types, or the contents of these sets rather, is information that is available to the type checker to verify that the program is going to do the right thing. So at the beginning here, remember we introduce our first location C, which is at the beginning of the region. So here, the end of the region is also the beginning. It's just this location C. And so far we have no constraints. We're not constrained anything. Right? And we have exactly one unwritten location. Right? So when we introduce the second location A, so now A is at the end of the region. We now have one symbolic constraint that C is equal to, or A is equal to C plus 1, right? And then now we have two unwritten locations. We've not written to either A or C, so they both belong in the set. So once we write our first leaf here to A is still at the end of the region. We still have the same constraint, but we've removed it from the unwritten set. We introduce this new location B. B is now at the end of the region. We have another constraint, and we now have these two unwritten locations. We write our second leaf here to B. Now we take B out of our unwritten set. And then finally, we construct the node. We have no unwritten locations left, and the end of our region is now C again. And we have these constraints. That makes sense? Right, so when the compiler is reasoning about the program, it's using types, and by using types, it means this information. This is what's available. Right? Okay, so finally, how do we prove things about this? Right? Well, we want to reason about the heap being well-formed. Right? And one way to talk about that is witnessing the ends of serialized data structures. Right? So how do we know a data structure is serialized in a valid way? Well, you walk through it and get to the end, following the rules of the serialization. Right? This is like, how do you recognize something? Well, you parse it, right? So given a type tau, a starting address RNI, and a store S, this rule asserts that there's an end of that serialized value, that if you were to parse it, you'd get to the end of it, right? And so it is always the case, right, in the semantics that for all of the pairs of locations to types in sigma, there should be an end witness, right, which written slightly more formally looks like that. And then finally, the dynamic side, the M and the S, and the static side, all these letters, these agree. So at every point, the type information and the runtime information line up, right? They never conflict with each other. So the types we saw on the previous slide and the picture on the even earlier slide, they never contradict each other, right? And that's proven. Okay, so we're done with the theory. Thank you for sticking with me for that. Now let's dig into the implementation. Okay, so I've spent all this time talking about serialized data. Well, what if I want to reintroduce pointers? Right. So as an example, let's say I have this list 2-1, and I want to cons 3 onto it. Right. Well, one thing I could do is return an entirely new list that contains 3, 2, 1. Right. So let's say we have this program here, let x whatever in node xx. So in ordinary Gibbon, this would be a problem, right? This would involve duplicating x. The compiler would have to do a full copy of it, right? But a straightforward translation would be to add this extra data type and make the second x an indirection. So now, if you would look at memory here, this would be, the node tag followed by the first tree, and then a pointer back to the first subtree again. Does that make sense? There's a little bit of thought here, in that if we swap these around, right? What if we put the ix before and then the plain x afterwards? That would be a little bit awkward because where would the pointer point? We haven't written that data yet. So that would actually not agree with our invariance. So we have to make sure that we've written the data once before we try to point to it. Okay, another thing to talk about. Full and partial traversals. So I've sort of glossed over a bunch of stuff, which maybe you've noticed. Maybe I've been doing such a great job you haven't noticed, right? But here's another function, sumTree. So the thing about sumTree is that it always traverses its input, just like add one tree, right? So we pattern match on node, we bind both the x and the y, then we recur on the x and recur on the y and sum their results. So a thing that happens here is we always process both the x and the y from the node, and we do it in the right order. So we don't have to process the y first and then process the x, right? So why is this interesting? Well, here's another function, rightmost. So rightmost returns the rightmost leaf in the tree, right? So again, we pattern match on the node, we bring x and y into scope, and then we just recur on the y and throw the x out. But remember, the x could be built with recursion. We don't know how big it is. So in order to get to the y, we have to jump over the x somehow. Right? So what do? Right? Well, if we're in control of the writing of the data, we can make sure that there's like a sort of jump pointer put in, like an offset in the buffer, so that after the node tag, there's a pointer to jump all the way over the x to the y. So that'd be one option. Another option would be to synthesize a traversal of x. So just build a recursive function, walks through x, doesn't do anything with it. And then that would get us to the end of x. Right? So which one's better? It depends on your use case, right? The compiler, if possible, will do the first option. It'll put offsets in the buffer. But if that's not available, it is able to generate a big traversal. And we have a paper that was just recently submitted to Uppsala. So ignore this if you're on the PC to Uppsala. I didn't say anything. Where we have a sort of global solver that will look at all the functions and all the data types and rearrange the fields based on how they're used in the functions to try to avoid this problem. Okay, so earlier I talked about these n witnesses that are used in the theory, right? They're also here used for sort of code generation, right? So we perform what we call traversal effect inference, where part of the function type is whether or not it traverses its inputs. Right? And so if a location is not traversed, then we have to compute its end witness somehow. So we have to do the computation of getting to the end of the data structure. Right? So why do we have to do that? So here's the next step of the compilation. We call this cursor passing code. We've thrown away all the types. Yeah, now we're getting very close to C. So I call this now add one cursor. It takes in and an out, just like that C code from the beginning. We don't have match anymore. Now we just have switch. So we're switching on what our input cursor is pointing to, like what tag it is. So it's either a leaf or a node. So in the leaf case, what do? Right? Well, we write a tag to our leaf, which gives us back this output cursor is sort of the next place, right? So we increment the pointer and sort of return the new pointer, right? We read an integer from the input, right, which gives us back the integer and the new pointer. Then we write the n+1 to the output, get a new output pointer, and then we return both of these pointers. Does that make sense? So what is the difference between this and the previous version of it? Well, now we're explicitly carrying around pointers to both the input and the output. And we're incrementing these as we go along. Right? So the node case here, right, we leave a space like we said we would. Then we recursively call add one cursor. And the result of the first recursive call gets passed into the second one. So why does that happen? Because the function is expecting these pointers to the correct places in both of these buffers. And then it returns sort of the end having read and written the right amount of data. Right? So the first invocation of add one cursor, this sort of gets us to the right place so that we can do the second recursive call. Does that make sense? Right? So like if this was some big, if at the point we are, at the beginning of this function, we have a huge subtree that's going to be handled by recursion. We call this recursive call. It walks the pointers all the way to the end of it, and then returns the pointer at the end. So it gets us to the end of that recursively built data structure. Right? So this is why we have to worry about computing n witnesses, is because we're going to generate this, which is then going to turn into C code. How am I doing on time? A little bit left.
Oh, yeah.
Okay.
10 minutes.
Yeah, okay. Yeah, I was not sure if I'd get to the parallel stuff. Okay. So one thing that we were interested in doing was combining all of this with parallelism, right? But if we go back to this example here, we're explicitly introducing a dependency between these two function calls, right? We have to do the left one and then the right one, because the output of the left one feeds into the right one. Which is a shame, because if you look at the original function we wrote, it was just obviously potentially parallel, because the two recursive calls had nothing to do with each other, right? So how do we reintroduce parallelism? Well, one of the issues here is allocating in parallel, right? So I have three examples here. The top one, all three of those fields for some data structure K are allocated sequentially. So we do field 1, and then field 2, and then field 3. Let's say we wanted to do 2 and 3 in parallel. So one thing that we could do is we could have the current thread handle field 2, have a different thread handle field 3, and then when they're done, we add a pointer to jump from the end of 2 to 3. Right? And if we wanted to do all 3 in parallel, well, now we just have 2 pointers. So that's it, right? Job done? Right. Well, what is the danger here, right? Is if we have a bunch of spawns in our parallel code, we're just putting pointers everywhere. So we've lost all the benefit of all the serialized stuff, right? So one of our insights was you don't actually have to do this, inserting of pointers and everything if on every spawn. You actually have to do it every time there's stealing in a work stealing scheduler, right? So you could have spawns all over the place, but only if the parallelism actually happens do you need to introduce this indirection in the memory, right? And it turns out that this insight plus our existing performance means that we have excellent parallel scale. So here's some comparison against Maple, OCaml, and GHC. There's 3 sort of programming languages that support parallelism with work stealing. This is, I will preface a little bit of an unfair comparison because we don't need garbage collection and they do. But still, The parallel plots, they go up and to the right, like a parallel plot should. Right, and then horrible tree or horrible table of data here, which you don't have to read, but I want to point to this part of the table specifically. It says x86 compiler. That does not mean compiling x86, even though it sounds like this is what it means. This is a simple nanopass compiler that targets x86. So this is one of our benchmarks, right? And if you look at the timing results across this table, right? And especially here at the end with GHC. So this GHC over R is 48. This means running on a computer with 48 cores, this benchmark is 10 times faster in Gibbon than it is in Haskell. So writing a compiler in Gibbon and parallelizing it is potentially very profitable in terms of performance. All right, okay. So now on to the conclusion. There are so far 3 big conference papers, which you can go read if you want any more detail about this. Potentially more, we'll see in a couple of days when the ICP reviews come out. And then again when the OOPS reviews come out. I'm hoping for good news on both of them. So I put the dates here because I wanted to mention this work originally happened back in 2017. Right, so this was one of my first conference papers as a grad student, and it's continued since then. Right, I haven't put like the workshop papers and talks and stuff, but this has so far led to 2 PhDs, including myself, which originally we did not think this was nearly that big of an idea. This was just a let's waste some time today writing binary tree traversals in Lisp. Right? Okay, so what are we working on now? So I mentioned we don't need a garbage collector, but what if we did? So one thing we're working on is garbage collection for mostly serialized heaps. So there are a couple of things that are interesting about this. Right? One thing is the collection phase of the garbage collector could actually compact and serialize things as it's collecting the objects. Right? And then there's a challenge on the other side, which is that we have all these things where objects are pointing to other objects, but they're pointing into the middle of them instead of at the beginning. Because not usually how garbage collectors work. So there are some challenges here and some potentially important things to do. Another thing, like I mentioned, is we're working on automatically optimizing the layout of algebraic data types. And this actually doesn't really interact with the location calculus stuff at all. Right? So we use integer linear programming to basically look at the entire program and all the data structures and try to rearrange things in memory to improve locality. And then finally, like I mentioned, the compiler, we're really interested in building interpreters and compilers that use serialized ASTs. Right? So one thing we have in mind is that we could potentially get some of the benefit of bytecode while maintaining the recursive structure of an AST. Right? If you want to use Gibbon, it is online. We have a website, one of those websites that GitHub generates for you automatically from Markdown. You can clone it. You can build it with Stack. It might still build with Cabal. I haven't checked. And then you can run some of the examples. Right? And that's it. I have my contact information here.
Some questions?
Yes. Cool stuff. You are doing a lot of work on locality. I understand it's a really important thing for CPUs because you're chasing pointers.
Oh, yeah.
And it's a big thing. And I would think that once you've solved that, maybe another thing is going to be branching.
Yes.
I was wondering whether these recursive formulations you have, can the CPU actually effectively predict the branches in those recursions?
Yeah, that's a good point. So and even related to that are the match states, the switches, right? There's potential problem there with the branching. Right. So yeah, so this is something we're interested in. And as people in this room know, there's a long history of converting recursive programs to iterative ones. Right. So we're really interested in that space. And if anyone has any ideas, I'd love to talk about that. That is like on the next steps. Yeah, to thinking about like when we generate C code, we're generating C code that does recursion, which is maybe not the best thing to be doing.
Yeah. Your examples used a flattened or partially flattened representation of concells.
Yeah.
But can you work with other sorts of serialization techniques?
Yeah, so okay, that's a good question. I should be repeating the question.
Yes.
Sorry about that. Okay, so the question was, we're working with the sort of flat representation of concells. Can we work with other forms of serialization, right? And the answer is mostly yes, right? Right now, there's some machinery in the compiler that is sort of specialized to pre-order serializations. So looking at an algebraic data type and essentially going like lexically in order. But that's not a hard restriction in the theory. Actually, the theory is sort of open-ended and is parameterized so that you can plug in a different serialization method and everything will still work. A thing that we're interested in is trying to match this to some like existing like published formats of binary serialization so that you can point this at like data that already exists. Yeah, that's the thing that we'd really like to do.
Yes.
I would wondering if this could be coupled with transactions, for instance, have some sort of implement some sort of database that already accesses the directly serialized data using memory mapped files, for instance.
Yeah. Yeah. Okay. So the question was, can we relate this to like transactions and maybe like a database that has the sort of memory mapped files? And I think that would be a great use case for this, actually. Yeah. Especially things that might involve a little bit of searching, right? Where you have some data and you want to walk through it. Another application that's related that this is good for is this allows us to sort of reason about pointing directly into the middle of some big data structure, right? If you have some sort of tree-like thing and you want to point it to like this exact spot, right? Now we have a way of doing that formally. Does that answer your question?
Mostly.
Mostly? Okay. Well. Any more questions?
I have one question
Mhm.
about the performance of the code,
Mhm.
because when you generate your nodes,
Mhm.
you first generate the left subtree, then the
Yeah.
right subtree, and then you come
Yes,
up with
yes.
the tag at the beginning.
Yes, I was hoping someone would ask this.
That's not
Yeah,
correct.
yeah, I was hoping someone would ask this question. Right, so everything in the theory requires that tag to be written last, right, all the way up until the end of the compiler, in which case we've thrown away the types, and we can do a simple dependency analysis and just flip that up to the top. So,
But that's done.
yeah, the compiler does that, yeah. And that's reflected in the benchmarks, yeah. I haven't actually benchmarked what effect it has. I assume it's
so
pretty
you don't
significant.
know exactly how much it-
Well, because we did it like without thinking. It's like, well, obviously you want to write the tag first. Yeah. Okay.
Okay, let's thanks because